Hi everyone, my name is Eric. I'm currently working as a software engineer at Microsoft Vancouver, Canada. I also have a YouTube channel called Eric Programming where I share coding interview and computer science related topics. Other than that, I also speak Mandarin and English. My mission is to help people to pass their technical interviews and get into their dream jobs. In this video, I'm going to walk you through 5 steps that I personally use when I go solve any software engineer coding interviews, as well as how to solve questions that I have never seen before. Now, the first step is to clarify the question. So here on the right, you can see we're given a question, right? And we're trying to merge all the linked lists into one sorted linked list and return it. So that's the goal. And in a real world scenario, maybe the interviewer might verbally communicate the problem to you. And your goal is to take the questions that are given and then try to maybe write it down on the text pad and try to confirm with the interviewer, right? And in this case, the first step, what I always try to do is to clarify what's the problem and also clarify what's the input and the output for the problem, right? Sometimes the interview might not give you an example, and it's kind of like your task to ask what's the input and what's the output, right? And here you can see kind of some questions, for example, like what kind of linked list are we talking about? Is it like circular linked list or is it like a singly linked list, right? Is it going to be integer linked list? Can it also contain like characters, right? Or strings or any other things, right? Or do we have to do any validation check, right? Can there also be like null value, right? So there are some constraints that we have to clear before we go into like what are some of the approaches, right? Now, after we clarify that these are the constraints, then right now is probably a good time to talk about the approaches, right? What are some approaches to solve this problem? And sometimes candidates might get stuck at this stage, so it's very, very important to focus on solving the smaller problem, right? For example, how to merge 2 linked lists, right? Forget about how to merge k number of linked lists. Focus on how can we be able to solve, or how can we be able to merge 2 linked lists. So for example, if I want to merge 2 linked lists, right, then in this case, I have two pointers that points to the head node for each linked list, and then we compare the value. In this case, they're all equal to each other, so we take the bottom one. And then in this case, since 1 is smaller, so we take 1, right? And then we move the pointer to the next node, right? And then 2 is smaller, so in this case we're taking number 2. And then here you can see 3 is smaller, so we take number 3. And then here you can see 4, they're all equal to each other, right? Then in this case we're just going to take any of them. In this case, let's take number 4, right? The top one. And then you can notice that one pointer is out of bound. So if that's the case, then what we can basically do is to have result.nest, right? In this case, is this result list right here is equal to either this sublist or this sublist. But ideally, we want to have the result list to combine or add the nest node to be this one right here. The result.nest is equal to this sublist, right? So in this case, this is what we do, right? We check which pointer is null. If it's null, then we basically get the result.nest is equal to that sublist, right? So that's kind of like, how we can be able to merge 2 linked lists. Now the problem is how can we be able to merge k linked lists? Now, similar approach about how we can be able to merge 2 linked lists, right? We first merge the first 2 linked lists. Once we merge the first 2 linked lists, right, we get a longer linked list. Then we can be able to use this linked list to merge the remaining linked list, right? So we can be able to merge all of them, right? And at the end, you can see the time complexity is k times n, where k is number of linked lists that we have in the lists, and then n is basically total number of nodes, right? We basically iterate k number of times, and then for each iteration, we basically merge 2 linked lists into one. So now the step 2 is to talk about the approaches, like I mentioned before. Now, of course, you might be thinking, okay, what are some ways to, further optimize this time complexity, right? And you might be stuck. Well, my other tip for this one is to think about what's better than big O of k times n, right? Of course, there are some algorithms or some big O notations that are better, right? That are faster than this one, right? For example, n log k or k log n, right? Or we can drop it down to linear where we have big O of n or big O of k, right? But that's not possible, right? So let's try to focus on, what are some of the ways to solve this problem or further optimize the solution using big O of n log k or k log n. Now, the first question is like, which one should we focus on, right? Should we focus on big O of n log k or should we focus on big O of k log n? Now, if you think about it, n is the number of nodes that we have in the entire lists, right? Like in this case, you can see we have 9 nodes, so n is equal to 9, right? But in this case, if we were to do log n, that means that we're only doing log n of nodes in the list, but we have to visit all the nodes, right, inside of our lists to be able to merge it. So this solution is not possible. So that's why we're going to focus on the big O of n log k, right? And we want to further optimize k, right? So before what we have is k times n or n times k. And now what we want to do is we want to focus on how we can be able to optimize this so that we can use log k, right? Now, in order to use logarithmic complexity, there's a couple ways, right? For example, we can use binary search, right? But the thing is that we're not searching anything, so there's no point for using binary search. And we can also use heaps, right? Heaps, we know that the insertion, deletion, or trying to find that the top element in the heap is always big O of k, right? Then in this case, what we can do is that we can use heaps or min heaps or max heap to solve this problem. To solve this problem using a priority queue or a min heap, what we can do here is that let's say we are given those two lists, right? So in this case, we can basically put them in a min heap so that the first element or the top element in the heap is guaranteed the smallest value, right? So we put the head node for each list, right, onto the heap. And then we say that this is the smallest value. And then we can just basically pop that value out of it, right? So once we pop that out, we only have one node inside, which is this one, right? So we pop that out, we add it onto the result list. And then we basically also know that this node has also a nest pointer. So we basically add this node onto the min heap. So we have 4, right? And then we know that this node is the smallest, so we pop that out. And then we know that this value is the smallest, so we add it onto the result list. And then this node has a nest node, which is 3, so we just add 3 onto it. And we know that 3 is smaller than 4, so 3 is the toppest element in the min heap, right? So once we basically add 3 onto it, right? We know that 3 is the smallest, so we pop that node out, and then we add it onto the result list as well. And then here we basically add the next node, which is 4, right? So 4 here, right? And then in this case, 4 is also the smallest, so we basically just pop that node out, right? And then we basically add that onto the result list. And then since there's no node that this node is pointing to, now we can basically just remove that, right? We don't have to add it back to the min heap here. And then here you can see we have our 4 here. And then for 4, in this case, you can see 4 is the smallest in the heap, so we just remove that out of the heap. So we basically add that to the result list, and then we basically move on to add this node onto the heap, right? Because this node is pointing to node 5, so we add node 5 onto the heap, and then node 5 is the smallest in the min heap, so we basically remove 5 out of it, and then we just point the result node on to node 5, right? Add node 5 onto the result list, and then here you can see we have nothing in our min heap, so our answer is this. So now you can see if we were to look at the approach that we're currently doing, right? Focus on using a heap, then the time complexity is going to be big O of n times log k, right? Because in this case, like I mentioned earlier, the heap insertion and deletion is going to be log k, and then the space complexity is going to be big O of k because we're only storing k number of nodes, right? Storing k number of nodes into the heap, and we're basically storing references, right? And then each node is pointing to the next node, so we're only storing the reference to the heap. So in this case, it's going to be big O of k for the space complexity. But of course, it's very important to consider about time, right? If you don't have much time, then of course, tell the interviewer that, hey, how about let's try to focus on writing the implementation and then focus on the optimization later, right? Or maybe we do have time, or maybe the interviewer will like us to continue to further optimize. Then of course, we will definitely try to, talk about what are some other approach, right, to solve the problem, right? What are some pros and cons for each approach, right? And of course, the other approach to solve this problem, right, is using divide and conquer, right? Of course, the problem with the current approach is that space complexity is big O of k, right? Can we further optimize the space complexity down to, for example, big O of 1 or big O of log k or something like that, right? Then in this case, we can be able to use something like divide and conquer, right? And the reason why here we're using divide and conquer is that because here you can see, since all the lists are divided already, and our task is basically to use like some kind of like merge sort, for example, right? Try to merge those two lists together, and you can see that the time complexity is still n, right, which is the number of nodes that we have, a log k, right? Because you can see here, we're basically merge these lists in a log k time complexity, right? When we try to merge back up, right, into a single list. And of course, the time complexity is going to be n log k, and then the space complexity here is going to be either big O of 1 or big O of log k, depends if we're using recursion, right? The recursion also count as the recursion stack, so that also counts as a space as well. But all in all, you can see that it's even better than what we have before. So maybe we can talk about that, right? Talk about the pros and cons. Like here, the pros is that, we can be able to further optimize the space complexity here, right? Step 3 is going to be focused on implementation, right? So to implement the code, right? For example, let's say we're going to implement the min heap solution, right? Then in this case, what I would like to suggest is to focus on the higher level implementation, right? Rather than focusing on the detail. For example, here you can see I basically trying to put or break this, right, by adding all the nodes into the min heap into a separate function, right? In this core main function, I want to focus on, what's the purpose, right? What's the goal that we want to achieve? We want to be able to add all the nodes onto the heap, and then we want to use heap to sort the nodes and then merge them together, right, into one single linked list. And that's the purpose of this function, basically delegating these tasks into a separate function so that these sub functions can be able to deal with it, right? So you can see here, we add all the nodes into the heaps, and then for this function, we're trying to use min heap to sort the linked lists, right? And here you can see in this way is more better because let's say we're running out of time, right? We only have like 10 to 20 minutes to code. Then in this case, we can be able to focus on just creating these functions. And then if we have time, we can come back and be able to fill these functions, right? You can see for add nodes, right? We basically adding all the nodes onto the heap. For min heap sort, we basically sort the min heap like this, right? So here you can see we can basically break it down into separate functions so that we can be able to focus more on the core function here. After we're done with our implementation, it's very important to test the code, right? When I say test the code, not just to like, click on the compile button just to compile to see what's the result, but of course try to, step through each and every single line of the code, and we're trying to, basically test the code with actual test case, right? So for example, here we have node 3 and node 1, and then in this case, the goal is we want to merge these linked lists into one single list node, right? To one single linked list. So now what to do first is we basically adding all the nodes to the min heap, and then here you can see after we add them, this is the result, right? So here we have node 1 and node 3, right? Added onto the heap, and the top element in the min heap is going to be node 1, right? And then we have our dummy node, we have our current node, right? And then we also have our min heap sort function. So we call this function, we pass in the min heap, we pass in the current node, and then you can see here for min heap, this is what it looks like. And then while the min heap is not empty, right? We basically remove the first element that we have in our min heap, which is this one. And then we basically say that current node.nest, which is equal to top, current node is equal to top. And then we say that current node.nest, if it's not null, right? Of course it's not null. Then we're basically going to say that adding the nest node, right, onto the min heap. And then for the next iteration, we know that min heap is not null because we currently have two nodes on the min heap, right? We have node 2 and node 3. So what we're going to do is we're going to take the top element, which is node 2, and then you can see we basically test it from there, right? And then in this case, since the current node 2.nest is null, so we're going to move on to the next iteration. And then the top element here is node 3. So we basically do the same procedure, and then we basically adding node 6, right, which is the nest node for node 3 onto the min heap. And then we basically continue to iterate, right? So basically try to step through the code line by line and trying to make sure that the test case that we're testing is actually working, right? And try to test code with a smaller test case, because if you're using a larger test case, sometimes it's very time consuming, right? So after we do the merge sort, right, or sorry, the min heap sort, we basically have a result, and the result is equal to dummy.nest, right? Because dummy node is just a dummy node, is just an empty node. And what we're basically trying to do here is trying to return the result, which is equal to dummy node.nest, which is this one right here. And then that's what we return, right? So for each line, we're basically adding a comment that this is the value that we're with our current test case, right? Now, after that, of course, there's also a chance to further optimize the time complexity or space complexity, right? So after we're done with the testing, of course, maybe we still have time, then it will be better to talk about what are some other ways to further optimize, right? For example, using merge sort or divide and conquer. How can we be able to use divide and conquer to solve this problem, right? If we still have time. Now, just to summarize everything that we talked about, basically, we talked about 5 steps to solve the problem, right? So for example, here, clarify the question, discuss about the approaches, what are the pros and cons for each approach, as well as implement the approach in code, right? Usually either in the text pad or in the HackerRank code compiler, right? And then you basically want to test the code line by line and figure out what's the problem, right? Make sure that the test cases that you mentioned in the interview works. And then talk about the optimization, right? What are the solutions? What are some other approach that we can be able to further optimize the time complexity or the space complexity, right? And the optimization can be done before the implementation, or it can be done after the implementation, depends on the time. Now, let's say you got stuck, for example, then my suggestion here is that to focus on solving the sub problems, right? Forget about, merging k number of linked lists. Try to focus on how can people to merge just 2 linked lists, right? And then build up the solution from there. And then also talk about optimization. Like, let's say if you don't know how to further optimize your solution, then think about what kind of or what other complexities that is better than the current complexity. For example, current complexity, we're using big O of n times k, then the next complexity that is better than n times k could be n times log k, right? Or k times log n, right? Or it could be linear time complexity like big O of n, big O of k, and so on and so forth.
Thanks for watching the video. If you liked it, please subscribe. Our website is prepfully.com. We've got lots of interview questions there. You can also schedule a mock interview with one of our experts. You can find the link in the description below. All the best from us at Prepfully, and we hope you totally rock your interview.